In the previous videos, we mentioned about the informations that are incorporated in the structural key plan. It was mentioned that the structural key plan is produced on basis of the architectural drawing, which you need to follow the identical grid line system as given by the architect, and you may refine the grid line as necessary for easy referencing by the contractors who's going to build the building. There is a high concentrations of the informations in the structural key plan, and it's going to be the reference point for all the other technical drawing as produced by the engineers. You need to provide sufficient details and informations regarding each structural element, their layouts, their design, their reference numbers, and etc. Other than that, there are also some important informations to be incorporated there, made known to the contractor, minimize their effort flipping through the structural key plan and the floor plan of the architect. If you provide those informations clearly, this will make them to be easier, and it's going to save them a lot of time. You must always keep in mind the purpose of you to produce the structural key plan. You want the contractors to be able to interpret your drawing easily. You need to make everything simple, easy to refer, neat, and easily to attain informations without much hassle. Due to so many informations to be incorporated in the key plan, extra effort will be required so that the drawing doesn't look messy, remove the irrelevance, minimize the redundancy, and also the repetitions. Now we're going to discuss in more detail specifically how you're going to produce the layout of the beam. There are many considerations. One of the important informations in the structural key plan, it will be the layout of the beam. When you are proposing the layout of the beam, there are many things that you need to observe. You need to ensure the integrity of the structures. You will need to be able to imagine how the beam will look like when it is in the reality. It must be something which is workable, and it should be stable. These are a few considerations that you can look into, where the beams are normally used to split the slab into smaller pieces, which normally not exceeding 8 meters of the clear span of the slab. You know that the slab is a plank surface which is laid horizontally. There will be a significant amount of concrete as compared to the amount of reinforcement. Normally, slab do not have problem with the shear resistance due to its large effective shear areas. The problem with the slab is there is limited effective depth, which is beneficial to resistance of the moment. The longer the span, the larger the weight of the slab, particularly when the slab is made of the concrete with significant weight. When the span is more than 8 meters, there will be excessive moment, and this requires additional reinforcements. It is likely to become uneconomical due to the limited effective depth of the slab. In resisting the moment, of course the beam is more effective due to its advantage of the larger possible depth. Therefore, you may use the beam to split the slabs so that the weight of the slab can be transferred to the beam and let the beam to withstand the moment. Next, you will need to make the slab to be square and rectangular. This is for easy analysis of the slab, unless it is inevitable, where the other shape of the slab can be applied. And normally when it is not square and rectangular, the analysis of the slab, it will be more heavily dependent on the modeling software. Square and rectangular slab is easy for you to analyze, where you can distribute the load based on the guideline given in the BS 8110 or you may use the U-line method for you to analyze the load, distribute the load for the design of the slabs, columns, and beams. There will be rise and drop on the floor slab, and normally in the existence of the drop or rise, there will beam at the edge. It will be something like this. When you have a piece of the slab and another piece of the slab, if without the beam, there will be concern with the structural integrity. You don't have sufficient areas to ensure these two slabs are in one piece. Sometimes there is a discontinuity, directly no regions of contact. That means there are going to be structural concern. To overcome this, you may apply a crossing beam here. This will give you a good drop while ensuring the continuity of the slab. The loads from the slab is distributed to the beam from the both sides of the slab, and this beam will serve as the support to the slab. When you use this method to connect the slabs, especially the existence of the drop, you have to be careful in terms of the difference in terms of the elevations of the slabs. If the difference is small, you might not have problem with the beam size. However, if the difference is quite significant, you will need to make sure your beam size is adequate to support the slab. This should be the right design, and this design going to fail. There is no direct connections between the beam and the adjacent slab. Normally we will put the soffit of the beam same level to the soffit of the slab. Another one is the existence of the beam are normally below the brick wall. Whenever you observe brick walls, normally will require beam to sustain the load due to the advantage of the beam in resistance to the bending moment because of its effective depth as compared to the floor slab. And I would say that the locations of the brick wall is one of the significant considerations that governing the layout of the beam. Next, the beams are sometimes used to connect the column, and normally we will prefer the connections it will be in two axes, as demonstrated in the diagram here. Let's say this is the column, this is the column, this is the column, here is a column, and here is also the column. The rest it will be the beams. To ensure the stability of the column, we will need the column to be restrained in both directions, the x-axis and the y-y axis. The beam will serve as the restraint to the column in reducing its effective length, which will directly govern the slenderness of the column, and this will significantly influence the amount of reinforcement bar required in the column. Therefore, you will like the beams to restrain columns in both directions. It's either all four sides you have beam, or you have beam for two directions. It may not be all four sides, but at least there are beams in both x and y directions. That means this kind of the arrangement, beam with the columns is okay, and if possible, we try to avoid this kind of arrangement where you have only one side of restraint while the restraint is not available on the other side. Same goes to this. However, sometimes this kind of arrangements may not be fully avoided, which normally we see this kind of design. It is when the upper story do not have any significant load. For example, the beams for the roof at the car porch only one story. There won't be column extended above the car porch, and the loads onto the roof of the carport is relatively small, then you might not have problem with the slenderness of the columns. Next, you need to consider the symmetrical layout of the building. If the building is symmetrical by definitions of the architect, that means the architect draw the building with symmetrical arrangement. Theoretically, your layout of the beam should also be symmetrical. This is for easy referencing as well as easy analysis. Your typical span for the beam, it will be somewhere between 3 to 6 meters. Very seldom for the normal usage. I'm referring to the typical residential, office or commercial building. Very seldom we have the beam more than 9 meters. The reason is when your beam section is more than 9 meters, you need significant height of the beam, which normally you will have problem with the headroom as well as the problem with the space available within the ceiling. This will require additional column to reduce the span of the beam so that it falls just nicely within the typical size used in the industry. And when you design the beam, the continuous beam is normally more preferred. If you can have the members to be continuous, that will be the best solutions, as you will not have significant moment at the midspan, where your support can be used to withstand some part of the moment, so that the moment happening at the midspan will reduce. There is formulas for you to analyze the loading acting on the continuous members and the simply supported member. I believe by now you should be very familiar with this. Another one is you need to be careful with the dropping slab along a continuous beam. Let's say now you have 3 slab panels here and you have a crossing beam here. The slab panel at the middle is slightly lower elevations as compared to the two. So when you have a crossing beam, you need to make sure these sections of the beam will also having the same drop in order to prevent the beam to stand up from the slabs. These are something that normally students overlook, that will lead to quite an awkward design of the structures. And then in terms of the design of the beam, if there are no columns in between, you will need to design the entire element to be continuous. There is a specific section here with a drop here due to the drop of the slab. That means there will be reinforcement bar on top of the beam as well as at the bottom of the beam. The reinforcement bar will need to be continuous. You cannot have your beam to be designed in this manner, as you're going to have problem with the connections between the beams. There is no continuity between the continuous beam here. Most likely it's going to fail in shear. The best way for you to design it, you will need to make sure the soffit of the beam for the entire continuous member, if there is no column in between, the soffit need to be at the same level. But if you have columns in between, then you are allowed to do so, because every single member here will now be considered as simply supported beam. This is a typical continuous member. If all the level is the same, that means you have no problem. You have to be careful with these conditions. These are the minor things that normally students overlook. That's why I said it is important for you to imagine in 3Ds. This kind of thing only appear after you finish the construction. Then you realize that, oh, something is wrong with your design. You need to prevent this to happen. You're going to check thoroughly your structural key plan against the architectural drawing. Next, you need to consider the beam size. That is another thing that you have to decide. normally pre-decided for you to start with the analysis. If the sections is undersized, through the calculations you will find some failures due to certain conditions of the loads or certain considerations on the structural aspects. When it is undersized, you will need to increase the size in the analysis later to ensure it reaches to the size that the beam passes in all structural aspects. Normally, you have to predetermine the size while you're producing the key plan. Only after you've done the analysis, which you conclude the beam size, then you come back and refine your key plan. Let's say now you overestimate the size of the beam. The implications it will be the design will be uneconomical. Normally we will do one more analysis with a smaller size, see if the beam section can be reduced, and observe the amount of reinforcement bar required within the beam. If the beam fails, that means the size that you used previously, that will be more economical, or that will be a right size for the member. Or if you see the reinforcement bar over congested within the beam, that means most likely the size is relatively small. You're going to require a lot of reinforcement bar. Probably you will need to use a bigger size. As far as the key plan concerned, especially during the first round you propose the key plan, because your key plan it will govern your analysis later. You at least need to have the first draft of the key plan. Then you pre-propose certain size. You need to take considerations in terms of the dropping surface of the continuous member, as mentioned just now, something like this. That means you will purposely oversize the beam here in order to ensure good continuity with the member here. You will need to consider the thickness of the wall, which sometimes the wall is made up of one layer of brick, or sometimes it will be two layers of brick. The typical width of the brick it will be 115. For two layers it will be 230. You're going to expect plastering from both sides. That the typical width of the beam it should be somewhere 150, used to support the single layer of wall, and you need to be 230 and bigger to support the double layer of brick wall. And the beam size, which specifically in terms of the depth, it will be governed by the drop distance between the adjacent slabs, as we have mentioned just now. Although the span is okay, you calculated the beam will pass, but you have to imagine the cross section of it. If the drop exceeded the size of the beam, you know that this is not going to be stable. You have to intentionally increase the depth of the beam. Next, you have to be careful with the alignment of the beam, especially in relative to the grid line. There are several conditions. The beam may be laid along the edge with the grid line, or the grid line may be at the center of the beam, or sometimes the beam is at the offset distance from the grid line. All this need to be clearly indicated in the key plan to avoid confusions of the contractors. They need to know the exact locations of the beam for them to be able to construct the building accurately. In the case that your beam is an offset distance from the grid line, you will need to indicate the distance from the grid line so that the contractors is able to locate the exact positions of the beam, as stated in the statement here. You will also need to be careful with the cantilever beam. This is another common mistake by our students. You know that cantilever beam is not stable by its own. You cannot arrange the cantilever beam in such a manner because the joint here will behave as if a pin joint, or slightly better, it will be semi-rigid. We cannot assume this to be perfectly rigid, and most likely if you have cantilever beam in this manner, your structure is going to fail. Unless your protruded length here is less than the width of the columns, or the protruded length here is less than the width of the crossing beam here, it is still possible to reinforce this kind of extended member. But when we talk about the cantilever beam, that means there's going to be a significant extruded length here, and this is not going to be stable. You will need to make the setup to be something like this, where there will be reactions from the column here, as well as the pulling reactions from the other column. In this case, the tension will be on top of the beam, and the compressions, it will be at the bottom of the beam. Therefore, when you arrange the reinforcement bar, you will need to make sure your tension reinforcement bar, it will be at the top of the beam. By all means, normally we try to avoid the cantilever beam, as this is going to require a lot of reinforcement bar. It is unless it is required in the architectural drawing, you have no other ways to support the slab or to support the beam, then you go for the cantilever beam. This definitely is going to be an uneconomical solution, and you should pay extra tensions on the cantilever beam. The local practice with the cantilever beam, normally they will over design it. And there's one more thing, you cannot allow the cantilever beam to be cantilever in both sides. For example, you don't have column here. You cannot expect the loading here will help to counteract the loops here to ensure the stability of the member. Or you cannot expect the column here or the beam here to provide resistance in terms of the rotation to ensure the stability of the cantilever beam. You know that the loading by nature, especially we are talking about the imposed load, it is something which is movable. It can be there, it can be not there. You cannot guarantee it's always there. Therefore, you must avoid the cantilever beam on both sides being supported by something at the middle. There will be a problem with the structural integrity.